employee tested positive, but they hadn't been on campus since, I think, May 3rd or something like that. So, or maybe it was April 3rd. So they're not worried about it. And went over last night and actually hung out for a long time. Somebody dumped a bunch of their, this is on Dirty IM. This is what I read, you know. Anyways, somebody, maybe Marty or I don't know, when they cleaned out their office, there's all this stuff in the break room. So I went in the break room to raid the refrigerator to see if there was anything good in there. And someone beat me to it. And then I found all these cool American Mathematical Monthlies and college math journals. So maybe Eduardo, you might want to look into that. I think when you're a student, you get a free membership to one of these things. You get little interesting articles.
Oh, it's just like the Math Monthly that I get. They give you like little snippets, right? Like they do in the newspaper with like people recent discoveries and stuff.
Kind of like the American Mathematical Monthly. That's like really serious papers. Like my advisor at UCI, he would have papers in there. In Mathematics Magazine, this thing, these are more just like, for example, the one I'm in right now is I'm looking at this article on quartic groups and how the old timers figured out how to solve fourth degree equations and stuff like that. And then there's the College Math Journal, and that one's pretty good too. So these are things for you guys maybe who are majoring in math to think about it. All right, so let's do the screen deal. And there we go. And one note. And there we are. Okay. I gotta turn this thing over. And I have to unplug it. This new rig isn't exactly what I thought it was going to be, but it is a little bit better. Okay, so let's see. Today we are going to be in section 7.4, and we're going to be talking about partial fraction decomposition. Okay, so this is a topic from Precalc that is, the last time I checked, was an optional topic. I don't think I did the partial fraction stuff with you guys that were with me. When would that have been? The fall, because I knew that we would eventually have to do it here. And you're a little bit more mathematically mature, to kind of get this. Okay, so I'm going to start with an example here. Suppose I was to add up these two fractions. Okay, we would common denominator it. It's going to be x plus 1 plus x minus 1. I mean to say minus, hold on. Minus. And then this, whoops. Okay. It's going to be x plus 1 minus then x minus 1 divided by x minus 1 times x plus 1. Okay. And when we simplify the numerator, we see that the x's go away. And so what we end up with is 2 divided by x minus 1 times x plus 1. Okay? which is 2, if you like, times x squared minus 1. Okay, now yesterday we learned the technique to handle an integral like this, right? We would have said, okay, x is going to be the secant of theta, and then we're going to go from there, okay? And however, because of what we just observed up there, that function 2 over x squared minus 1 is equal to 1 over x minus 1 minus 1 over x plus 1. Okay? Now, I ask you, which integral would you rather follow the path of? This guy? Or this guy? Or this guy? This guy, look, we got to go dx is secant tan. And we're going to have 2 secant tans divided by tan squared. So that's going to be secant over tan. Maybe we'll finish that one up later. But the point of this whole thing here is that this is now very easy. This is the natural log of x minus 1 minus the natural log of x plus 1 plus a constant c. Or if you like, you can combine it up into x minus 1 over x plus 1 plus a constant c. Okay, so this is a very popular test question of mine. Wink, wink. Okay. And that being said, when I put it on the test, and I even put the 2 in there, I don't know if I'll do this for you guys because everything's different now, but I put the 2 in there just so these numbers end up becoming 1s, okay? Now, when you follow this through, you're not going to get exactly this. There's something else that's going on. Let's see if I was follow the 2 dx divided by x squared minus 1. X is secant theta. Okay, so it's going to be the integral of 2 secant theta tan theta d theta divided by tan squared theta. And that's 2 integrals. And then it's going to be the secant of theta divided by the tangent of theta d theta. And that's a 2. And then it's going to be 1 over cosine theta times sine theta over cosine theta d theta. We end up once again with this cosecant theta d theta integral. And I remember how this goes. It's negative the natural log of cosecant theta plus cotangent theta plus constant c. Okay, now for our substitution, theta, the secant of theta is this divided by that. Then you complete this guy, x squared minus 1. So I'm going to get, there's a 2. Okay, there's a 2. Now it's negative 2 natural log of the cosecant of theta, which is going to be x squared minus 1 divided by 1, time plus the cotangent of theta, which is 1 over the square root of x squared minus 1. And this is not looking a whole lot like that, is it? Okay. Did I make any mistakes here? I'm not trying to. 2 dx, 2 secant tan, Secant squared minus 1 is tan squared. 2 secant over tan. Here's secant. There's divided by tangent. There's the 2 right there. And now this becomes the negative 2. And cosecant, once again, is, oh wait, I screwed the cosecant up. The cosecant is x divided by x squared minus 1. And maybe you can combine those two guys into one happy fraction, which is going to be x plus 1 divided by the square root of x squared minus 1 plus a constant c. Again, it still does not look like that guy up there. Let's rewrite it down here. Natural log of minus 1 over plus 1. That's what we got. Okay, well, maybe if I move the exponent to the inside. Okay, so this would be the natural log of x squared minus 1 divided by x plus 1 squared. Now you see that it's coming together, right? We factor, and what we're going to get is, well, let's do this. Okay. Screen. Okay. All right. So after factoring and doing all that stuff, what we see is we get the same answer. Okay. Now clearly the first method is a lot quicker. All right. And so the question here is, can we always do this? Like the question here goes as follows. If we're given some function, let's say it is the product of a couple of linear factors, can we find numbers a and b such that this 1 over ax plus b times cx plus d equals a over ax plus b over cx plus d. It would be a lot easier to do the integrals because this is just going to be some kind of a natural log integral. It's going to be like 1 over a times the natural log of ax plus b. And then this guy would be b times it. Okay. All right. And if so, like, how would we do it? Okay. So we need to start with, and this is an explanation of why this is always going to work. Okay. So,
Professor,
yeah.
so could you go up and I didn't understand why you wrote ax plus b and cx plus d. Why did you take that specific form?
Just two general linear things. See, back up here when I first started the problem, okay, the integral was 2 over x minus 1 times x plus 1. That's like ax plus b, cx plus d.
Okay.
So I'm just saying in general, is this going to be doable? Okay. And the book does not give any kind of an explanation whatsoever for this. Okay. And there's a reason for that. It's because it's beyond the scope of, I mean, it's beyond the scope of, it's a senior level topic is what it is, maybe even in grad school. But I'm going to try to do this the best I can. Okay, so let's start off with numbers. Let's say I had 1 over 2 times 3. Can we find numbers A and B such that 1 over 6, which is 1 over 2 times 3, is equal to this times that? Can we find A and B? Okay. Well, this needs to be an identity. It needs to hold all of the time, okay, for A and B. We're not solving an equation. So if I cross multiply everything here, I'm going to get 1 equaling 3A plus 2B. So if we were to pick A equal to 1 and B equal to negative 1, we did. Okay. How about if we did this with 1 over 12? That's 1 over 3 times 4. So A over 3, B over 4. So what we get is 1 equals 4A plus 3B. And once again, we're going to let A equal 1, B equal negative 1, and it keeps working the same way, all right? All right, now what would it look like if I did the 5 over 12? Well, what you would do is you would write it as 5 times 1 over 12, and then do all of this business to the 1 over 12 and multiply the whole thing by 5. Okay? All right, so another way to factor 12 would be to go 1 over 2 times 6. And so that's like A over 2 plus B over 6. Cross multiplied through, and 1 is going to equal 6A plus 2B. Okay, try as you might to find the A and B, you're never going to find them. Anybody want to tell me why? Remember, A and B are supposed to be positive, or A and B are supposed to be integers. All right, Eduardo. Notice that I can factor a 2 out of this. 3A plus B. No matter what 3A plus B is, when you multiply it by 2, it's an even number. This is even, and this is odd.
So it only works with odd numbers?
Well, what I'm saying here is that it looks like it didn't work. Okay?
Okay.
All right, let's keep investigating this. Okay? So what if we had like 1 over 18? And instead of writing 18 as 2 times 9, I would write it as 3 times 6. Okay? So that'd be A over 3 plus B over 6. Cross multiply again, and you're going to get 1 equaling 2A. I mean, not 2A.
6A.
Multiply both sides, and you're going to get 6A plus 3B. Again, I can factor a 3 out of this, 2A plus B.
Mm-hmm.
Once again, it doesn't matter what this number is. This is always going to be a multiple of 3. Is 1 a multiple of 3? Nope. So there's no possible solution to this. Okay, now let's look at where it worked. Okay, it worked with 2 times 3, Maybe it worked with 2 times 3 because 2 and 3 are prime. Maybe. Okay. It worked with 3 and 4, but 4 is not prime. Okay. But if we compare some things here, these two guys are not only prime, but they don't have any common factors. These guys don't have any common factors either. Maybe the reason that this failed with 2 and 6 is because 2 is a factor of both numbers. Okay? All right, so in a number theory course, and trust me, there's a reason I'm doing all this, what we would learn, and I guess maybe like once Art retires, I think I might take over the discrete math class and just have some fun with it, do some number theory stuff. Okay, so here's a definition. We say 2 integers are relatively prime if 2 integers a and b are relatively prime if the greatest common divisor of a and b is 1. Okay, so they don't necessarily have to be prime, but they're like prime to each other in a sense. Okay. All right. Now, back sometime around, I think it's 400 BC. I think that's the time of Euclid. Okay. Euclid came up with a division algorithm for integers. And what he came up with, which is called the division algorithm, if we were to let a and b be positive integers, then there exists a Q and an R with the magnitude of R less than B such that A is equal to Q times B plus R. Okay, so now we have superior notation to Euclid. Shit, there's the button. Am I back in?
Yeah.
We can't see this. There we go.
Sharing the screen?
Perfect.
Yes.
Okay, we got it? All right. Okay, so here's what this is saying, really. If you divide both sides of that equation by B, divided by B is going to be this quotient plus this remainder piece. Remember that? Okay. So another way of saying this is B going into the number A gives you this Q, and then when you get all the way done, you have this R, and you remember that the R is got to be less than the B. Okay? And actually it works for negatives as well. All right. So.
Hey, Bobby, before we move on, could I ask a quick question just because I was thinking about this? On the last example you showed us where it was 1 over 3 times 6, you had 1 equals 6a plus 3b, and you said that there's no solution. But why couldn't the solution be a equals 1 and b equals negative 5/3, which would still equal 1?
Because we want a and b to be integers.
Oh, sorry. I apologize. Yeah, I was just running through solutions in my head. Okay, yeah.
Yeah. Now, there's a reason I'm doing this. sticking with integers. Yeah, you're right. We can find A and B to make that work, but not integers.
Okay.
That's kind of key. All right, so this Euclid division algorithm, which you probably started doing this stuff, you know, and I don't know, what grade are you in when you start long dividing? You go 23, you know, and do, let's say, 9,846. And then you ask, okay, how many times does 23 go into 98? Is it going to go in 4 times? I think that's going to give me a 92. We do the subtraction, we get a 6, bring down the 4. And is that going to go in 2 times? Nope, just the 1 time. 23.
I think it
Wait,
was
why would it
twice.
go in 2 times? That would be 46.
46.
46. 46. Do the subtraction, and we get 18. And then bring this guy down.
We're looking at 8
And
times.
8, maybe?
Yep.
4.
184.
There we go. Okay. And this bringing back terrible memories for you guys. Okay.
I like long division.
Anyway, the way that you learn this, you know, in maybe 4th grade, is you say 9,846 divided by 23 is equal to 428 with a remainder of 2. Or in 5th grade, the next year, you go do this stuff again, and you start writing it like this: 2 over 23. Okay? Now that's notation that I hate. Okay? Instead, it should be properly written as 428 plus 2 over 23. And I wish I could speak at an international congress of elementary school teachers who teach math. And I would tell them, you have to stop this shit right now. Okay? You have to put a plus in there because it's going to be confusing for people that don't have an aptitude in math and can separate things.
Yeah, because then you're multiplying.
Right. Okay. And the big thing about all of this is that the number 9846 is equal to this quotient thing. That's the Q. This is the A times the B, which is the 23, plus the 2, which is the remainder. And notice that R in magnitude is less than B. Okay? Just like Euclid said it would be. Okay, now from this, we have the next result. It says if we're given 2 integers, M and N, such that M and N are relatively prime, then there exists integers A and B such that A times M plus B times N equals 1. Okay, now in abstract algebra and in number theory and all this stuff, this is huge. If you can make a 1, you can make anything. Okay? And so if we follow this, let's look at, given this M and N relatively prime, okay, I want to split up 1 over M times N as some number over M plus some number over the N. Okay? Well, remember what 1 is? 1 is equal to AM plus BN divided, and that's what 1 is, divided by M times N. And then if we unadd the fraction, what we see is we get, I used the wrong letter, A, and that's B. What we get is we get this number A over, 1 over A over M. Well, anyways, A over N. And then this guy, when I unadd the fraction, it's going to be B over M. Okay? And so, oh, wait. I did have I was using the right stuff. Okay? 1 over M times N is equal to AM plus little bn divided by mn. And so that is equal to A over M plus the B over the M. I mean, the A over the N. And then the B is over the M. Okay, and so our big A is that guy, and the big B that we were looking for is that guy. Okay, so that was a whole bunch of number theory. All right. Now, the reason that I did all of this is because of the following useful information. The symbol that we use for integers is this bold Z. Real polynomials the notation mathematically that we use is stands for the set of all real polynomials. If I wanted to restrict the coefficients, like let's say I wanted only integer polynomials, I would have, done Z square brackets X.
Professor,
Yes.
I'm sorry to interrupt, but the thing about, could you explain that again?
Okay, so after the division algorithm, there is a result that I'm not going to prove for you here. Okay. It says that if two integers are relatively prime, you can find other integers, A and B, such that this sum can be made to equal 1. Okay, so now...
So using those prime numbers, the multiples of those prime numbers, and the sum of them could be 1.
They're relatively prime to each other.
Oh, okay.
As long as M and N don't have any common factors, you can always make a 1.
So it's like two prime numbers.
And it turns out, if their greatest common divisor was 2, you can find A and B to make it 2. Okay?
Oh, okay.
Okay, now that's just extra stuff. All I'm trying to get to is this right here. Okay? That we start off with 1 over M times N, but 1 is equal to this thing, and then I just unadded the fraction.
Oh,
okay, so as mathematical objects, the ring of integers and the ring of real polynomials are very similar to each other. Okay? Eduardo, they're both called PIDs, or principal ideal domains. Okay? Now, what that means is not important. Okay? It would take a whole bunch of abstract algebra. But what it does mean is that these rings enjoy shared properties. Meaning, if you have a concept in Z, like some concept in Z, like a number being prime, there is a corresponding concept in R square brackets X. Okay? So, for example, we have this concept of an integer being prime. Okay? Prime in R square brackets X is going to mean something similar, okay? So like the number 5 is prime because its only proper divisors are 1 and 5. You cannot factor 5 into 2 smaller numbers, okay? So this concept of being prime within polynomials would look like this. Let's say I've got my polynomial f of x equaling 2x plus 3. Now I ask you, can you factor this? Okay. Now, what is the answer to can I factor this? Somebody that knows the answer. How about
You can break it up into a piece.
Eduardo? You have to. What do I say about factoring all the time?
That it has to be.
Did I say, is this going to factor? Yes. Why?
Yeah.
Because everything factors. Okay? It just might not factor nicely. If you guys remember in Math 180, in order to evaluate some limits, we had to get medieval with our factoring and do shit like this. Okay? So this polynomial, I could factor into similar stuff like that, but these things don't count as polynomials. Okay? So this thing is prime in R square brackets x. And for that matter, the primes in R square brackets x are functions of the form ax plus b and ax squared plus bx plus c, where the discriminant is negative. That's it. Everything else can factor. So, like I'll challenge you here, right here. This guy is going to factor. Okay? And it's going to factor into 2 real polynomials. All right, now maybe you can give this a whirl and stuff like that, but the way you do it is you would say, okay, it's going to have to be, it can't be x cubed because this guy doesn't have any real roots. And you remember the root theorem, if p of a is 0, then x minus a is a factor. So this would have to be x squared plus some number x plus 1, x squared plus some number x plus 1. And if you put an a and a b in here, what you find is that you get square root of 2 and square root of 2. Okay? So the only kinds of polynomials that do not factor are linear polynomials and quadratic polynomials with a negative discriminant. Now, if we change our real to complex polynomials, then yeah, we can factor because we'd be able to use i's and stuff. All right? All right. And there is the analogous result for R square brackets x. And if I say a of x and b of x are polynomials, there exist polynomials q of x and r of x such that a of x is equal to this quotient polynomial times this b of x thing plus this remainder polynomial. Okay? And from this, we then get the analogous next result. If a of x and b of x are relatively prime, then there exists guys, which I guess we'll call m of x and n of x, such that m times a plus n times the b of x is equal to 1. Okay? And so because of that, we can now say the following result. Okay? If a of x and b of x are relatively prime, there exists, let's say, m of x and n of x, where 1 over a of x times b of x is equal to the m of x over the a of x plus the b of x over, the n of x. That's the chalkboard. N of x over b of x. And here, the degree of m is less than the degree of a. The degree of n is less than the degree of b. Okay? All right. So, for little linear problems, like the following, let's say I wanted to integrate this function. 1 over x squared minus 3x plus 2. Okay? Now, one approach we could use is to complete the square, get rid of that 3x term, make the u substitution for the new variable, and then do trig substitution. Okay? That seems to be a bit much. So the 1 over x squared minus 3x plus 2 is equal to 1 over x minus 1 times times x minus 2. Come on, right? Yeah. Okay. And so because x minus 1 and x minus 2 are relatively prime to each other, we know that there are polynomials out there, a and b, such that I could bust this up like this. And furthermore, the degree of a is less than the degree of x minus 1. Well, the degree of x minus 1 is 1, so that means that the degree of a, and for that matter, the degree of b, are both 0. That means they're numbers. Okay? So now we need to find them. So we'll just do what we did back with the integers. We'll cross multiply. 1 is going to equal a times x minus 2 plus b times x minus 1. There are many different ways to find the a and b here. We could line it up as a polynomial equal a polynomial, but this has to be true for all x's. So if it worked for some x here, it would certainly have to, if it works here, it works here. So let's pick x equal 1. If I did that, I get 1 equaling negative a. So that means a is negative 1. And if I let x equal 2, 1 is going to be b. So the b is 1. So that means that this is 1 over x minus 2 minus 1 over x minus 1. And therefore, the integral of that would just be the natural log of this guy minus the natural log of that guy. And this generalizes. Okay. So if we've got this function f of x equaling 1 over, and then I'll say a number of these, a1x plus b1, a2x plus b2, where all of these guys are relatively prime, a nx plus b sub n. If all of these are relatively prime, it's going to be broken down a1x plus b1. And then there's going to be an a2 divided by the a2x plus the b2 dot 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 plus an divided by anx plus bn. And all of the a1 through an's, they are all integers. Their degree is less than that. Okay, and each one of these antiderivatives would be pretty easy to handle, don't you think? You know, it's just some kind of a logarithm thing. Okay. Now let's see. Let's try an example and see what happens. So I want to integrate, excuse me, let's say dx divided by 2x minus 1 times x plus 3. Okay, let's say that I multiply that out and you figure it out, you can factor it. Okay, nicely. So we're going to take our 1 over 2x minus 1 times x plus 3. And because these two things are relatively prime to each other, Euclid didn't actually prove this. He proved that you could do this with numbers, and then it got adapted to polynomials when it was discovered early on that polynomials are principal ideal domains just like integers. All right, so now you cross multiply again. 1 is going to be a times x plus 3 plus b times 2x minus 1. Okay, so I can use convenient numbers here. Let's say if x is equal to negative 3, 1 is going to be negative 7b. So b is going to be negative 1 over 7. And then if x is equal to a half, 1 is going to be a times 7 halves. So a is going to equal 2 over 7. So now that means this is the integral of 2 over 7, 2x minus 1, plus negative 1 over 7 times, divided by x plus 3. Okay, so if u is the bottom, du is going to be the 2 right there. So this is going to equal, eraser here. This is going to equal 1 over 7 natural log of 2x minus 1, and then minus 1 over 7 times the natural log of x plus 3. Okay, so this partial fraction decomposition is a pretty clever trick. Now, if I'd have shown you this back in pre-calculus a few months ago, last year, whenever, because we can't really go anywhere with it and not do these hard intervals, it seemed like it might be impossible before we discovered this. I don't think you would have gotten anything out of that. You know, I would have been telling you, hey, it's going to be really cool when we get to Math 185. Well, you know, that's 2 classes away. So anyways, because we have to cover it here, I just think it's better to do other things in pre-calc. Okay, now let's say we also have an irreducible quadratic down there in the factor, in the denominator. Like, for example, my function f of x is going to be 1 over x times x squared plus 4, let's say. So we were asked to integrate 1 over x cubed plus 4x. Okay? Okay, so these guys are relatively prime. And so there exists numbers such that this is going to equal a over x. Now this is where things get a little more interesting. What you have to put up here is bx plus c. Okay, now there are a lot of details, weeks and maybe even months of details that I left out in the story when I started, with the relatively prime and make it equal 1 and this and that and the other. Okay, the degree of this a has to be smaller than 1. So that means it's a number. Okay, this denominator right here is degree 2. The thing that's the most general thing that's smaller than degree 2 is degree 1. And so that is why that goes there. Okay, now maybe after lecture or some other time, I could go into it a little more deeply, all that stuff from, way back up here. Okay, but not everybody wants to hear it. But I do believe you do deserve an explanation, because all these calculus books are the same. They offer no information. Okay, so we would say that 1 over x times x squared plus 4 is equal to that. Again, cross multiply. 1 is going to be a times x squared plus 4 plus bx plus c times x. Okay, so if we let x equal 0, we're going to get 1 equals 4a. So that a equals 1/4. Okay, so now 1 equals 1/4 x squared plus 1 plus bx squared plus cx. Okay. Now, there's no x squared over here. That means there must be no x squared over here. So the b is going to have to be negative 1/4. And the c is going to have to be 0, because there's no x on this side. Okay? And so what we find is our 1 over x times x squared plus 4 is equal to a 1/4 over x plus the b negative 1/4 x divided by x squared plus 4. And so the integral of this thing, x cubed plus 4x, is going to be 1/4 the natural log of x. Okay, and then it's going to be minus, okay, u is a du, so it's going to be minus 1/8 the natural log of x squared plus 4, plus constant c. Okay? Partial fraction decomposition. All right, now the way that this kind of, goes in general, if I just gave you some random 5th degree polynomial, you're probably not going to be able to factor it if it was random. Okay, all of those weird ones that you were able to factor in Precalc, those are all set up ahead of time to be factored. Okay, finding roots to degree 5 and higher equations, it's been proven, there's no formula. So a lot of times you have to do some approximating. So a lot of these integrals end up becoming approximated. All right. All right, now, repeated roots. Generally, in the normal class setting, like if we were all in 163 right now, the explanation above with all of the integers, I go a little deeper with it because I can leave more stuff on the board and point to it and so on and so forth. Okay. But when it comes to the repeated roots, I don't really have a good explanation for you. Okay. For why we're going to do what we're going to do. So let's say that our function f of x has like these not repeated roots, repeated factors. Okay. Let's say x minus 1 cubed. Okay, so what you do here with this is you go a over x plus 1 plus b over x plus 1 squared plus c over x minus 1 plus d over x minus 1 squared plus e over x minus 1 cubed. And then you go to find the a, the b, and the c, and the d, and the e. Okay, now the reason for this, again, it has something to do with a result called the Chinese remainder theorem. Discovered on a piece of some kind of parchment over in mainland China many years ago. There's this reference to this. It basically has to do with what are the possible remainders you can get when doing stuff. Once the topic of abstract algebra took off, that number theory result, which was the Chinese remainder theorem, that's what everybody calls it, CRT, got applied to polynomials at a very deep level. Okay, so again, there is no integer analog for this. Okay, the ring of integers is not identical to the ring of polynomials. The ring of integers can be generated by just one integer. One. You start with the number 1, I can get any other integer I want. But that's not true with polynomials. If I start with x, I can get any polynomial with x, but I can't get it with x squared. So now I got to throw in an x squared and start over because x and x squared are treated as like apples and oranges. Okay? And if you have repeated roots, repeated factors that are irreducible quadratics, like f of x equals 1 over x squared plus 1 squared times x minus 2, let's say, you have to do the ax plus b over x squared plus 1. Then you have to do another cx plus d divided by things squared. And then the e over x minus 2. These things become real pains in the butt. All right. So let's maybe walk through this particular one and see. We cross multiply the thing out. 1 is going to be ax plus b times x squared plus 1 x minus 2 plus cx plus d times x minus 2 plus e times x squared plus 1 squared. Okay, so we'll be able to get the e pretty easy. Let's say if x is equal to 2, then everything wipes out. 2 squared is 4. 4 plus 1 is 5. 5 squared is 25. 25e. So e is going to be 1 over 25. Okay. Now, here's one for you. What if I let x equal I? Am I allowed to do that? Well, turns out you are, okay? Even though we're dealing with real polynomials, you're allowed to do this. So
This is because we're using x, right? So
we're using what?
it's because we're using x.
Yeah, I'm just saying that, see, I know if I plug I in, this is going to wipe out and that's going to wipe out.
Yeah.
And so here's what I would have. 1 is equal to ci plus d times I minus 2. Now we're just going to equate two complex numbers, okay? Ci times I is negative c minus 2ci plus di minus 2d. That's what 1 is. So negative 2c plus d has to equal 0. And negative c minus 2d has to equal 1. Okay, so if I multiply by this 2 and add, I'm going to get negative 5c equals 1. So c is negative 1/5. So then 1/5 minus 2d equals 1. So 2d equals negative 4/5. So d equals negative 2/5. Okay, so I've got E, I've got C, and I've got D. Okay, so I still need to find A and B. So let's see here. We can use, let's plug everything in. This is where it's really better to have the board. Okay, so ax plus b, and then this is going to be x squared plus 1, x minus 2. Okay, now the c was negative plus. Negative 1/5 x minus 2/5 times x minus 2, and then plus 1/25 times x squared plus 1 squared. If I let x equal 0, then 1 is going to be negative 2b plus 4/5. X is 0 plus 1/25. Okay? And so what is that going to be? 1 equals negative 2b, and then that's going to be plus 21/25. So 2b equals negative 4/25. So the b is negative 2/25. So there's the b. All right. Now that's probably the gnarliest example that we have. But if I go back up here and start including it, let's see. The f of x equals, okay, the a was what? Or did I not even find the a yet? Nah, shit, I still got to find the a. Okay, let's see. How about if x equals 1? So 1 is going to equal a plus, whoops, minus the b, 2/25 Okay. And then times 2 and times -1. And then plus negative plus 3/5. And it's 1, 2, 4 over 25. 4 over 25. Okay. So 1 equals -2a plus 4 over 25 plus 3 over 5 plus 4 over 25. So 2a is equal to -25 over 25 plus 4 over 25 plus 15 over 25 plus 8 over 25. So whatever that number is. 19, that's it. 23, 27, 52. No, that's not right.
A equals 2 over 50.
2 over 50 or 1 over 25? Okay.
That's what I'm getting.
All right, so 1 over 25. Okay, so back up here, here's what we would be trying to integrate. 1 over 25x. The b was what? -2 over 25? Minus -2 over 25 over x squared plus 1. The c's and the d's are on those first, right? -1/5, -2/5. -1/5 x minus 2/5 divided by x squared plus 1 squared. And then the e, which was the 1 over 25, divided by x minus 2. Okay, now, here's how we would integrate this. We would unadd the fraction. The first guy, this is a u substitution right here. This is just straight tan inverse here. This is another u substitution for this guy. This one, you're going to have to use trig sub on for this over this. You'd have to let x equal tangent, but it's doable, okay? And then that's just the logarithm of x minus 2. Okay, so that is about as ugly as I think it's going to be in the exercises for you. And again, we don't really have a good explanation for why it works, but it's so important that we want it to work. Okay, so let me take one out of the book. So they want us to integrate. Let's see here. Looks like it's the integral of x squared divided by x minus 3 x plus 2 squared. Dx. Okay, so one thing that we need to make sure of is that we're always dealing with proper fractions. Okay, so like I said, there's concepts for everything. Size in integers means absolute value. Size in polynomials means degree. The degree of the denominator here is 3. The degree of the top is 2, so that's a proper fraction. If you don't have a proper fraction, what you're going to do is do long division and get that quotient, which is a polynomial, plus this remainder piece, which is what I call the nugget. And that's the thing that you're always working on, okay? So this is some nugget that we got left over with. So we'll do our x squared over x minus 3 x plus 2 squared. That's going to be a over x minus 3 plus b over x plus 2 plus c over x plus 2 squared. Now here, a, b, and c are all going to be numbers. These integrals are real easy. That's the a log of x minus 3 plus b log of x plus 2. And then that's going to be c time divided by, that's going to be negative c divided by x plus 2. But we need to find the a, the b, and the c. So we'll start that process right now. And we'll say, all right, x squared, this time it's different. We're starting off with x squared on the top. This is going to be a times x plus 2 squared plus b x minus 3 x plus 2 plus c times x minus 3. Okay, so let's see. Let's let x equal negative 2. Then 4 is going to equal negative 5c. So c equals negative 4/5. When x is equal to 3, 9 is equal to 25a. So a is 9 over 25. Okay? Now we don't have anything left to wipe stuff out. Okay, so let's just pick another value of x. X equals 0. 0 is going to be 4a. Okay, so that's going to be 36 over 25 plus b times negative 6. So let's do that. Minus 6b, and x is equal to 0 minus 3 times the c. So that's going to be plus 12 over, what was I doing? A is 9 over 25. So x equals 0. I get 36, 25 minus 6b. The c is negative 4, so it's going to be 12 over 5. Okay, so 6b is equal to 36 plus 5 times 12, which is 60, over 25. So this is really out of hand here. 6b is, I guess, 96, 25. So b is, the 6 go into 96?
32 times.
32?
30.
B is equal to 32 over 25.
No, sorry. No, I'm way off. It doesn't. Sorry. That
16, 20.
16 would, 16 would be right. Sorry. Yeah, I was way off. Sorry, guys. 16. I think it's it.
16 times 6 equals 96. Okay, so it's going to be 16 over 25.
804. No, 804.
What?
No. Sorry, my bad. Sorry. No.
16 over 25. Okay, so our integral now is going to be the a, which we found to be 9 over 25 x minus 3, and then plus the b, which is 16 over the 25 times the x plus 2, and then plus the c, which is the 4 over 5 x plus 2 squared dx. And now this is just 9 over 25 log of this thing plus 16 over 25 log of this thing. And then this is going to be x plus 2 to the negative 1 divided by negative 1. So that's going to be 4 over 5 over x plus 2 plus a constant c. Okay? These things are they can get fairly messy. The way that I do them is I start off with what I want. So like the way I'll generate the test question, like I want the A, B's, and C's to be ones and zeros and stuff like that. So what I'll do is I'll take something like this. Let's say 3 over x, and then I'll add the fraction, common denominator it, and then that's the thing I'll put on the exam. Okay. Now, again, he does have a problem in here. Let me make sure we all understand this. Early on, he's got a problem like this, where he's going to have something like r squared over r plus 4. Now, what he wants you to do first is you have to divide, because we don't have a proper fraction. Okay, so r squared plus 4r, subtraction negative 4r, bring down the 0, minus 4, minus 4r, minus 16, subtraction 16. So what this integral is the quotient plus this remainder piece, which is the nugget. And that's the thing that you have to integrate. Well, you have to integrate the other stuff too, but polynomials are easy. So like, for example, if I wanted to integrate, let's say, x cubed plus 1 divided by x squared plus 1, let's say. Step 1, I got a long divide, okay? And so you would go x squared 0x plus 1. Remember, there's no synthetic division for bigger than linear. This is x cubed 0x squared 0x plus 1 x cubed 0x squared, x do the subtraction, and x bring down the 1. So this is the same thing as the quotient plus the remainder piece. Okay? And you would break it up into two separate integrals. X over x squared plus 1. 1 over x squared plus 1. And then it becomes x squared over 2 plus 1/2 the log of x squared plus 1 plus the tan inverse of x plus constant c. Okay? All right, so in this guy, the exercises go clear up to number 68, okay? And there's a couple other things that we need to talk about in this section before we leave it, okay? So when we have square roots in equations and things we're trying to integrate, like let's say we wanted to do this integral of x, square root of x plus 1 over x. Okay? So if you let u be the radical underneath the radicals, not really going to get you very far. Okay? You can try, but the choice that we're going to make here is we're going to let u be the entire radical. Okay, so that means u squared is x minus 1. So x is u squared minus 1. Dx is 2u du. And square root of x plus 1 plus 1 minus 1. Yeah, that's right. Okay, so the integral now is going to be u times du divided by u squared minus 1, which is 2u squared divided by u squared minus 1. Okay? And so if we were to do this trick here, like so, then this is going to be the integral of 2u squared minus 2 over u squared minus 1 plus 2 over u squared minus 1. And so this is going to be now just a 2 plus the 2 over the u minus 1, u plus 1. And if you remember, that was like the first partial fraction thing we did. It's 1 over u minus 1 over u plus 1 du. Okay? And so now we just go 2u plus the log of u minus 1 over u plus 1 plus constant c. Now we got to remember what u was. U was the square root of x plus 1. So it's 2 square roots of x plus 1 plus the log of square root of x plus 1 minus 1 square root of x plus 1 plus 1 plus constant c. Okay? Okay. Any questions on that problem? No?
Professor.
Yep.
So how do you determine what to take in x when you split the partial fraction as ax squared plus bx plus c or ax plus b? Yeah.
You meant, how did I know to do that?
Yeah, how did you know to do that, and how did you know what to take x as c? So you've written x equals 2 and x equals I. So
Okay, well, the x equals 2, it's because it's going to, if I let x equal 2, it wipes out all of this, and it'll let me get e. Because this has x minus 2 and x minus 2. Now, as far as why this is the way it is, it's what I told you. It's because of the Chinese remainder theorem.
Okay.
This is the most general remainder you can get when dividing by x squared plus 1. Okay, so it's an abstract algebra topic that's kind of complicated. Okay, now our last bit of stuff for tonight we'll talk about rational functions of sine and cosine. Okay, so like for example, maybe we would like to integrate something like this. 1 over 3 sine x minus 4 cosine x dx. Okay, so long time ago, a guy named Carl Weiserstrass came up with a trick for these kinds of things. Okay, so for the substitution, I'm going to let t be the tangent of that x in there over 2. Okay? So t is the tangent of x over 2. Okay, so if I write the angle x over 2 in here, this is the tangent of x over 2. This is going to be the square root of 1 plus t squared, right? Okay, so from this, we see that the cosine of x over 2 is going to be 1 over the square root of 1 plus t squared. The sine of x over 2 is going to be t divided by the square root of 1 plus t squared. Okay? All right, now we need to get cosine of x and sine of x, not of x over 2. Well, the cosine squared of x over 2 is 1 over 1 plus t squared. And the cosine squared of an angle is 1/2 plus 1/2 the cosine of twice the angle. So that means that 1 plus cosine x is equal to 2 divided by 1 plus t squared. So cosine x is going to be 2 minus 1 plus t squared. I'm adding fractions in my head. It's just something to do. Okay. So I'll write this nicely here. We figure out by using the half angle formula that it's going to be 1 minus t squared over 1 plus t squared. Okay? Now, in order to get the sine of the x, we could draw a triangle and try to figure out how that's going to work. Or we could say that the sine squared of x is 1 minus the cosine squared of x. So the sine squared of x is going to be 1 minus t squared divided by 1 plus t squared. This is 1 plus t squared minus 1 minus t squared all over this common denominator, 1 plus t squared. And then we'll multiply the whole thing out, 1 plus 2t squared plus t to the 4th minus 1 plus 2t squared minus t to the 4th. And
isn't that minus 2t squared plus t4?
I made a mistake somewhere.
Oh, no. You took the
one
minus
let me
inside.
see.
Got it.
Yeah. 1 minus 1. So the sine squared, all of this is over 1 plus t squared. So the canceling, combining gives 4t squared over 1 plus t squared. So that means that the sine of x is going to be 2t divided by 1 plus t squared. Cosine of x, if you remember, was 1 minus t squared over 1 plus t squared. Okay, now the only thing left for us to do is figure out what dx is. Well, remember, we let t equal the tangent of x over 2. So that means that x over 2 is equal to the tan inverse of t. So x is equal to 2 tan inverses of t. So that dx is now going to be 2 divided by 1 plus t squared. Okay, so these are the important ingredients. And what Weierstrass realized, and of course he figured this all out in his head, okay, what he realized was that any rational function of sine and cosine could be turned into a rational function, because the field of polynomial fractions is complete in the sense that you'll never get fractions inside of fractions. You can always deal with it. Okay, so that problem that I wrote down, I think it was the integral of 1 divided by 3 sine x minus 4 cosine x dx. So this is going to be, it's supposed to be a dt. It's going to be 2 over 1 plus t squared dt, and then divided by 3 sine x, which is 6t over 1 plus t squared, minus 4 cosines, 1 minus t squared over 1 plus t squared. And notice all of those 1 plus t squareds are going to go away. So 2 dt in the top, and then in the bottom is going to be 6t minus 4 plus 4t squared, which is going to be dt divided by 2t squared plus 3t minus 2. And we now need to factor it. Okay, so 2t, t, let's see, I need a 2 and a negative 1, right? I think that gave me 4. Yeah, that worked. Okay, so a over 2t minus 1, b over t plus 2. So 1 equals a times 2t minus 1 plus b. No, the a is getting the other guy. A gets t plus 2. B gets 2t minus 1. Okay, so if we let t equal negative 2, 1 equals negative 5b. Seems like I've been doing a lot of problems today with 1/5. Okay, and if t is equal to a half, 1 is going to be 5 over 2a, so a is 2/5. Okay, so this is the integral now, back to the integral, is 2/5 over 2t minus 1 minus 1/5 over t plus 2. Okay, so u is 2t minus 1, du is 2 dt. So this is going to be 1/5 the log of 2t minus 1 minus 1/5 the log of t plus 2. T plus 2. Okay, now t was the tangent of x over 2. Okay, and so to wrap it up, you plug that in. 1/5 the natural log of 2 tangents of x over 2 minus 1 minus 1/5 the natural log of tangent of x over 2 plus 2. All right, so that was fairly complicated. Okay, but Weierstrass, the guys, the names we remember through history, he thought that all up in his head. It's kind of an interesting thing to do.
There's no constant speed for this stuff?
Did I forget? Oh, yeah, plus constancy. -1 for Bobby. Okay, so anyway, let's see how many people hung out today. Oh, 52, that's pretty good. All right, so now we're now at the end of techniques, okay? So on Monday, we're going to look at the next section, which is just basically an anything goes section. And, if you're in 7.1 doing an integral, the strategy to use is integration by parts because you're in that section. But in 7.5, where it's anything goes, he's got 81 questions. Okay, you might as well start this over the weekend. All right, do all of the integrals for the partial fraction stuff, and then get into these in 7.5. I take lots of test questions out of here. Okay, some of these problems are fairly difficult. So on Monday, we're going to spend a whole bunch more time doing this. Okay. All right, so let me take a break real quick and use the restroom, and not going to lecture anymore, so we'll just hang out and see you in about 10 minutes. Let me go take the...
I'll be gone, man, but you have a good day, okay? See you over the week. Have a good weekend, man. See you, Eduardo. See everybody else.
Later.
Thanks, Bobby.
Some employee tested positive, but they hadn't been on campus since, I think, May 3rd or something like that. So, or maybe it was April 3rd. So they're not worried about it. And went over last night and actually hung out for a long time. Somebody dumped a bunch of their, this is how nerdy I am. This is what I read, Anyways, somebody, maybe Marty or I don't know, when they cleaned out their office, there's all this stuff in the break room. So in the break room to raid the refrigerator to see if there was anything good in there. And someone beat me to it. And then I found all these cool American Mathematical Monthlies and college math journals. So maybe Eduardo, you might want to look into that. I think when you're a student, you get a free membership to one of these things. You get little interesting articles.
Oh, it's just like the math monthly that I get. They give you like little snippets, right? Like they do in the newspaper with like people recent discoveries and stuff.
Kind of like the American Mathematical Monthly. That's like really serious papers. Like my advisor at UCI, he would have papers in there. In Mathematics Magazine, this thing, these are more just like, for example, the one I'm in right now is I'm looking at this article on quartic groups and how how the old timers figured out how to solve fourth degree equations and stuff like that. And then there's the college math journal, and that one's pretty good too. So these are things for you guys maybe who are majoring in math to think about it. All right, so let's do the screen deal. And there we go. And one note. And there we go. Okay. I gotta turn this thing over. And I have to unplug it. This new rig isn't exactly what I thought it was going to be, but it is a little bit better. Okay, so let's see. Today we are going to be in section 7.4, and we're going to be talking about partial fraction decomposition. Okay, so this is a topic from Precalc that is, the last time I checked, was an optional topic. I don't think I did the partial fraction stuff with you guys that were with me. When would that have been? The fall, because I knew that we would eventually have to do it here. And you're a little bit more mathematically mature, to kind of get this. Okay, so I'm going to start with an example here. Suppose I was to add up these two fractions. Okay, we would common denominator it. It's going to be x plus 1 plus x minus 1. I mean to say minus, hold on. Minus. And then this, whoops. Okay. It's going to be x plus 1 minus then x minus 1 divided by x minus 1 times x plus 1. Okay. And when we simplify the numerator, we see that the x's go away. And so what we end up with is 2 divided by x minus 1 times x plus 1. Okay? Which is 2, if you like, times x squared minus 1. Okay, now yesterday we learned the technique to handle an integral like this, right? We would have said, okay, x is going to be the secant of theta, and then we're going to go from there. Okay? And however, because of what we just observed up there, that function 2 over x squared minus 1 is equal to 1 over x minus 1 minus 1 over x plus 1. Okay? Now, I ask you, which integral would you rather follow the path of? This guy? Or this guy? Or this guy? This guy, look, we got to go dx is secant tan. And we're going to have 2 secant tans divided by tan squared. So that's going to be secant over tan. Maybe we'll finish that one up later. But the point of this whole thing here is that this is now very easy. This is the natural log of x minus 1 minus the natural log of x plus 1 plus a constant c. Or if you like, you can combine it up into x minus 1 over x plus 1 plus a constant c. Okay, so this is a very popular test question of mine. Wink, wink. Okay. And that being said, when I put it on the test, and I even put the 2 in there, I don't know if I'll do this for you guys because everything's different now, but I put the 2 in there just so these numbers end up becoming 1s. Okay. Now, when you follow this through, you're not going to get exactly this. There's something else that's going on. Let's see if I was follow the 2dx divided by x squared minus 1. X is secant theta. Okay, so it's going to be the integral of 2 secant theta tan theta d theta divided by tan squared theta. And that's 2 integrals. And then it's going to be the secant of theta divided by the tangent of theta d theta. And that's a 2. And then it's going to be 1 over cosine theta times sine theta over cosine theta d theta. We end up once again with this cosecant theta d theta integral. And if I remember how this goes, it's negative the natural log of cosecant theta plus cotangent theta plus constant c. Okay, now for our substitution, theta, the secant of theta is this divided by that. Then you complete this guy, x squared minus 1. So I'm going to get, there's a 2. Okay, there's a 2. Now it's negative 2 natural log of the cosecant of theta, which is going to be x squared minus 1 divided by 1, time plus the cotangent of theta, which is 1 over the square root of x squared minus 1. And this is not looking a whole lot like that, is it? Okay. Did I make any mistakes here? I'm not trying to. 2 dx, 2 secant tan, secant squared minus 1 is tan squared, 2 secant over tan. Here's secant, there's divided by tangent. There's the 2 right there. And now this becomes the negative 2. And cosecant, once again, is, oh wait, I screwed the cosecant up. The cosecant is x divided by x squared minus 1. And maybe you can combine those 2 guys into one happy fraction, which is going to be x plus 1 divided by the square root of x squared minus 1 plus a constant c. Again, it still does not look like that guy up there. Let's rewrite it down here. Natural log of minus 1 over plus 1. That's what we got. Okay, well, maybe if I move the exponent to the inside. Okay, so this would be the natural log of x squared minus 1 divided by x plus 1 squared. Now you see that it's coming together, right? We factor, and what we're going to get is, well, Okay. Screen. Okay. All right. So after factoring and doing all that stuff, what we see is we get the same answer. Okay. Now, clearly, the first method is a lot quicker. All right. And so the question here is, can we always do this? Like the question here goes as follows. If we're given some function, let's say it is the product of a couple of linear factors, can we find numbers A and B such that this 1 over AX plus B times CX plus D equals A over AX plus B over CX plus D. It would be a lot easier to do the integrals because this is just going to be some kind of a natural log integral. It's going to be like 1 over A times the natural log of AX plus B. And then this guy would be B times it. Okay. All right. And if so, like, how would we do it? Okay. So we need to start with, and this is an explanation of why this is always going to work. Okay. So,
Professor,
yeah.
so could you go up and I didn't understand why you wrote AX plus B and CX plus D. Why did you take that specific form?
Just two general linear